Hi folks, welcome to this tutorial. I'm going to talk about logistic regression, the binary classification technique in machine learning library. And then we want to consider it, on, let's say, on two parts. First part, mathematical insight to see how we can use math to have this logistic regression in place. And then the second part, we want to go through PySpark machine learning library to see how we can apply it on large scale data. So I think you got the point. Logistic regression, no difference between let's say different type of data, either small size, medium size, large size. You just need to grab the idea behind this logistic regression, and then you can apply different libraries for a specific data. All right, in this case, we want to work with huge size data, and then we want to consider PySpark machine learning library. So how does it work? So let's recap linear regression, guys. If you're still new on regression, please watch my video about linear regression. So in linear regression, we had, let's say, independent variable here, x. Let's consider here one variable here we have. And then here we have y, which is dependent variable that we want to predict. All right. So we want to predict something continuous here. Let's say the speed of a train, the size, the height, the progression, something which is continuous, having decimal value. So if we have these data points here, all right. So after going through, some mathematical calculations to calculate linear regression, at the end, we need to find this straight line. And this straight line is going to be, from now on, is going to be the representative for this, for this data points. And whenever we have new data like this one, this is a new, let's say not this one. So if you have new data, right, like this one, that you have that dependent variable, this y1, you can map it to the line. All right, and then you can find what is the value. All right, this is the prediction. We can do that. So it works for a continuous variable, but in logistic regression, the topic and the idea is we want to predict something which is not continuous. This district means this is integer, but in this case is binary, true or false, 0 or 1, yes or no, non-spam or spam. All right, it's going to be binary. So for this one, you can see that you need to put your x as independent variable, and then these are y, right? This is y that we have two values, true, false, 0, 1, yes or no, good or bad. All right, so for this scenario, linear regression, it's not working, right? In the best case, this linear regression is going to be something like this. So you can see that how errors comes over there, right? We cannot use it. So what we can use, you need to, make this a straight line, like a curve line. All right. And then this curve line is going to, work like, let's say it's going to work like this, for instance, the curve line. Let's see how does it work. So if you want to consider logistic regression, as I mentioned, we need to find this curve line. All right. And this curve line works based on probabilities. We need to have a threshold, 0.5. All right. And then whenever you find this curve line, we need to map. Let's say I want to map this data to this line, curve line. You can see that it's going to be, let's say it's going to be something like 0.90. This is a probability. It means that the minimum one is 0 and the maximum one is 1, the maximum value, and threshold 0.5. Anything above 0.5, we consider it class 1. All right, you can see that it's class 1. So and like for this one, even for this one, still, the classification is right. But if you want to consider this one, it's going to be here, the mapping, and then the mapping says that, okay, this is less than 0.5, means this misclassified. So also for this one, if you map it to this line, it's going to be now above 0.5, above the threshold, means this is going to be to be in class 1. But we know that this is belonging to class 0 and also is misclassified. So we need to avoid these misclassifications. All right, how we can do so, let's discuss. So firstly, we need to find the mathematics behind it. So for, for this linear one, we had this, y, beta 0, beta 1, intercept, and a slope, right, that we calculated. For this probability one, which is logistic regression, you need to move it here, right, in the exponential format. So beta 0 is exactly this b, we call it bias, all right, and this beta 1, which call it weight, right? So this bias and this weight helps to find how this curve will be, like very, straight and sharp and tall, this S, let's say this curve or S shape, or it's gonna be like very soft, right, and very long from both sides. So that's the reason we need to tune this B and width that we want to discuss shortly. So as I mentioned, we need to find the best curve, right, to find out let's say there is no misclassification. So let's say we do start with this one, all right, and then over the training and over the optimization that we want to discuss shortly, what is this optimization? We need to move it right in this case, all right, to be able to find out, okay, this is the best one, all right. How to find this is the best one? We need to come over through these steps. So let's say that we have two x or two independent variables. So because of that, we need to define this, weights to 0. So these two weights, guys, come from here, right? We discussed here, but here we have just one x, right? One uh, independent variable. But here, let's say we have two independent variables. It means that we have to say w1 x1 plus w2 x2 plus bias. All right. So we need to initially put everything, here 0. So learning rate, because we need it for training for optimization that we want to discuss shortly. And we started with a small value 0.01 and number of iteration, guys. We need iteration to make sure that we take this, curve, move forward, right? Or let's say left side or right side, make it, like tall or make it short, make it longer. And to do so, we need to go through some, some iterations, and default is 100 in machine learning library. So step 2, as usual, for any machine learning modeling, you need to replace drop missing values, normalize data type conversion, outlier detection, feature selection, or whatever you have, you need to apply on the pre-processing data. So now we have to come over here, step 3. The main part that we have to calculate is gradient descent, or also you can call it batch gradient descent. So we need to go over this, number of iteration, let's say 100 times, and do and iterate these 5 steps, one by one, to be able to find the best curve line. So how does it work? So firstly, we need to calculate this linear regression. Perfect. Once we do that, we can move this z after calculation here, calculate the exponential, and find y prediction. Let's say that you have, for first data, you have label 1, all right, and also you could predict here 0.9. We have to consider, how is that good? All right, if you want to see how is that good, that it was 1, but now you predicted 0.9, we need to come over here, step 3, and we need to take over one cost function to calculate how the model is performing, well or bad, right? So we call it log loss. All right, this is the cost function. The aim is minimizing the error. Okay, how does it work? So log loss is going to say that we have, this minus of, this calculation. Let's say your label is 1. Okay, if your label is 1, so here you can see that this one is 1, and 1 subtract by 1 is 0, then this side, the right side, this one is going to be 0, because it's going to be 0 multiplied by something. So in this log loss, if your if your calculation, your data belongs to class 1, it means that for label 1, we need to always calculate this one, minus log and then y prediction. All right. And let's say that if your data belongs to class 0, right, and then this one will be 0, left side will be 0, and then this one for class 0, you have to always calculate minus log 1 subtract by yp. All right, two direction for class 1, class 0. So, I mean, that example we had, let's say you found y prediction 0.9. So how is that performing well? I mean, log minus log 0.9 is going to be, if I'm not wrong, is going to be minus point, let's say it's going to be something like this. So, and then it's going to be point, 105, 0.105. So the aim is to get this log loss close to 0. If it's close to 0, that you can see is close to 0, it means it is really a good outcome, right, for the first data. All right. So, but for second data, let's say that your label was 1, still you have to take over the same formula, and your y prediction you did here, it's now 0.1. All right, you did this prediction. So you need to calculate how is performing well. So then we have to calculate minus log, right, 0.1 is somehow, is going to be minus of minus 2 something. Let's say 2.3. It's going to be 2.3. So 2.3, guys, is far from 0, right? It means it's not really great. So we need to calculate this log loss for every single, data points, and then calculate the average. We would like to get average as minimum as possible. If it's as minimum as possible, it means you had really the best outcome, the best S curve, right, or best S shape on your data, regardless of how misclassification would be. But this log loss is really great. Even you can take this log loss as a stopping criteria over 100 times iteration on your data. If you get, the same log loss after a few iteration, means, I mean, is over, right? There is no well enough room, to improve the results. So after log loss, so here, guys, a few people, considering some other cost functions here, all right, or a loss function here. So like mean square error, guys, mean square error is very useful for regression tasks, basically for linear, for continuous data, not for discrete, not for binary data for prediction. All right, and few other like hinge loss, a square hinge loss, exponential loss. Guys, these are other type of loss function. All right, like as I mentioned, hinge, right? Hinge or square hinge. So, but this hinge loss usually we use it for support vector machine, SVM techniques, all right, not for logistic, because I mean, uh, this, let's say hinge loss or its variation like exponential one or like a square one that we use them for some other techniques. These might be suitable when you have a clear margin of a separation, all right, between classes. And basically these log loss work well when you have not really, the clear margin between data points, and like there are lots of up and down, like I mean, you cannot easily find, the great separator for your classifier. So in summary, log loss remain the most appropriate choice for most binary classification. All right, guys, because because it does probabilistic output calculation. That's the reason that we need it, for binary classification. So then after all these calculations, all right, once you have done all this calculation, so we need to come over here and move forward with this, I mean, find the updated bias and updated weight. Okay, 1 divided by number of items or number of data, the summation of y prediction subtract by y, And same, for this one. At the end, we need to update. How to update? The previous value, subtract by learning rate, multiplied by this dv we found how, or dw, we found it here, and so on. So with this one, you can have this curve line sharper, taller, stretch, and uh, with all this calculation, you can find, this curve line is gonna be like tall, right? It's gonna be short but long, right? Because bias and weight can help to do all this stuff. So this this learning rate, very important. Also, this is what we have to tune. So out of this, what we can tune, the tuning here happening on this learning rate, right? Because this is the hyperparameter. This is the parameters that we as an end user, we have to enter here. So if you put it too low, the gradient descent algorithm will make very slow progress toward the minimum of the of this loss function. All right, so maybe it takes longer during training time. To get a prepared result. And if you put it too high, so the algorithm might overshoot the minimum. Not really good, right? Resulting in let's say diverge and possibly fail to find a good solution. So you can see that is the challenge here. So, but the best and the good start for this, learning rate is might be starting from point one, or maybe point, 1, and maybe these are the good to start, right, for adjustment. Of course, there are some other techniques that you can tune this learning rate using grid search, using learning rate schedule. Guys, you can take them as a note. Maybe you can do this stuff, at your spare time. Adaptive learning rate, like adaptive moment estimation, ADAM or ADAM. So let me write them, here. So let me. So for tuning, that's going to be the additional consideration here. You can consider grid search, learning rate schedule, or you can use ADAM, or you can use, this RMS probe, right? We call it root mean square propagation. But basically we use this ADAM for deep learning task. All right, this one. And we use this RMS Pro. We usually use it for recurrent neural networks. All right. Or maybe you can use meta-heuristic algorithm. Guys, these are optimization techniques to discuss how we can optimize learning rate. I mean, uh, 0.1 is the best one, or this one is the best one, or this one is the best one. So which one is the best? You need to do by try and error, or use this optimization techniques. So step 4, what we need to do after performing all this stuff, let's say after 100 time iteration, you can achieve to the, let's say, the optimal result for weights and bias. All right, and then you can add them here for prediction. Let's apply this one on real data. Let's say this is our data, right? 3 data points class 0, 3 data point class 1. So let's get, the first data, this one, and calculate those 5 steps. So first step. So you can see that it says W, we said that initially 0 multiplied by 1.2, this one. 0 multiplied by 0.7, so it's going to be 0. So at the first stage, everything is 0 because W and B, they are all 0. Then step 2, we need to predict. What was the prediction? We need to use this one, right? 1 divided by 1 plus exponential of 0, 1, so minus 0, 1. So you know that these are all 0, right? The first step. The first step, same prediction. The third step, gradient descent, guys. We need to calculate loss, loss, and you need to calculate all over, for other, I mean, uh, data points here, because guys here, uh, because here we apply over 6 data. Because I'm applying over each data. The second step is going to be 2.1, it's going to be this one, right? The third one, 3.52, right? is going to be this one, because we said that at each iteration, you need to run this calculation over your data, basically training data. Here we have all 6 data. And then you need to find, this updated version. All right. And then to see how you can do so, 1 divided by the number of numbers. So we had 6 numbers here. The y prediction 0.5, y is going to be 0, x1, right, and so on. We need to do all these calculations. And then you need to update the weights. Okay, update the weights. These are really important, okay, for prediction purpose. Let's say after 100 times running this algorithm back to back, you find out this, output. So these are weight 1 and weight 2, right? And this is bias. All right, means that 1 point is going to be here, it's going to be here, and bias is going to be here. And then you need to put it here. So for prediction, great. So let's say new data comes over. This is new data, 4.8 and 2.9. We have no idea about the classification. Is it either 0 or 1? Is it either spam or non-spam? How? We have this one 1.34 multiplied by this x1, 0.86 multiplied by this, and subtract by bias. And then once you calculate this one, it's going to be this value, minus 1.7 something. Once you calculate this one, you reach out to this. More than threshold, right? Threshold is 0.5, so it's belonging to class 1. Guys, we could predict it, right? We could predict this one. You can do same thing for this one. So 2.4 here, 1.8 here. So because these are constant, right? And then you could calculate it by this 2.436. And the result is this, less than 0.5, belonging to class 0. Right, we could predict. So these are all great, right? We could predict, but still we need to discuss about performance, right? How this model works well, right? We need to work with confusion matrix, which is the table to provide the performance of your classification algorithm. How does it work? We have true classes and predicted classes. It means that positive means class 1, negative means class 0, right? Positive, this is a prediction, 1, 0. It means that true positive means that your true class is true, means is 1. Or let's say something like this. True positive means that you correctly predicted as positive, right? It means that true comes from this one and positive, for this one. Even for this one, true negative, it means you could successfully predict it as negative. All right, because this is the classification. I mean, this is a prediction, and negative is going to be for this one. False positive means that you wrongly detected as positive. It means that the prediction is 0, right? And you wrongly predicted as positive. And of course, for this one means you wrongly detected as negative, right? Because it's negative, you wrongly detected as negative. All right, this is how we can classify into 4 parts. So true positive, you can find, this keywords here, very useful, and you can consider. So we have some additional quantitative evaluation metrics based on those, these 4 parameters, true positive, let's say TP, FP, TN, and FN. So for instance, accuracy is going to calculate the number of correct classification. You can see that true positive means you could correctly predict it as positive, means class 1, and true negative you could, detect it correctly as class 0, divided by all the prediction, either true or false. It's called accuracy. Precision is going to consider only true positive, means you could predict it correctly to the positive, or let's say the class 1 label, divided by all of them, either true positive or false positive. We call it precision. And recall is going to say that same as precision, considering true positive, but here is going to say, okay, those true positive that a few of them correctly classified, and those ones that should be true positive, but you incorrectly detect them as negative. All right, or F score, the harmonic mean of precision and recall. Guys, you can use all this combination to detect, or let's say to provide the performance of your model. We will discuss this stuff, in the coding part. So let's say this data we used, right? These are y and these are prediction. So 3030 means, here true negative should be 0. 3 ones and 3 ones. You could put it here, right? Because we could classify correctly. And false positive and false negative 0. It means that this is perfect classifier, right? This is a perfect classifier without any misclassification. Let's get few exercises. So let's say you have two classes. All right. So we expect to this side be class 0 and this side be class 1. So let's find true positive and true negative. So true positive means that the label is, the label is 1. Also, you predict correctly. You can see that you could predict them correctly, right? 3 will go there. All right. So true negative should be this one, right? You could correctly predict them as 0, right? 4. So false negative, it means you incorrectly detected negative, means this one. 1 should be here. And false positive means that you incorrectly detect them as positive, means these two ones, okay? And then you can put it here. So, and then you can calculate, accuracy and so on. For accuracy, for instance, it says here true positive and true negative, right? True positive and true negative means 3 plus 4 divided by all total, right? It's going to be 10. It's going to be 70%. 70 means that accuracy is 70%, right? Because we have 3 data points misclassified. All right. So second one, so we expect to be class 0 and these are class 1. So true positive means you detect correctly. So 1, 2, 3, 4, right? 4 will be go there. True negative, you can see that 2 would be here. So false positive means you incorrectly detect them positive, 3. All right. And false negative means you incorrectly detect them negative. There is nothing, right? So it means it's 0. Okay, it's good. So it means that if you want to calculate, let's say precision, all right, precision, the precision said that true positive, all right, true positive plus uh plus false positive, all right. So true positive is going to be 4 divided by 7. All right. Or maybe, for other factors you can calculate and consider this classification. So this is about, the mathematics inside and how does it work going through confusion matrix. In the second part of this video, we're going to go through Google Colab and implement this logistic regression plus this confusion matrix using PySpark machine learning library. See you guys soon. Welcome back, everyone, to this tutorial. So in this part, I'm going to go through logistic regression using PySpark machine learning. So as usual, we need to install PySpark. So make sure to run this cell. And in the meantime, guys, please make sure to download this source file from the course page or from the description of the video. And you can practice while watching this video. So then, as usual, as we discussed, before even in the linear regression class, we need to, go through a few libraries and Spark initialization to have an interface called Spark. So please make sure to watch my previous videos if you're still new on this configurations. So we need to also ask for interface. All right, Spark, still PySpark is going on and the latest version will be there, and then Spark interface driver will be there, and then we need to work with data, right? We need to get data. So as usual, I would like to get connected to Google Colab and import Drive to be able to connect it to Google Drive. So this is what we need to do. And you just need to give permission and provide this permission. All right, So then we need to work around with data. So in this tutorial, I'm going to work with KDD comp data. So KDD comp is I mean, basically used for intrusion detection system, and this is a benchmark data that we can basically use for intrusion detection system. And of course, this data provide two type of classification. Uh, Multi-label classification, we will discuss it in the next video, and one more is binary classification. That's going to be like 0 or 1, means normal traffic and attack traffic. So if you want to if you want to go through this data, right, you can go through this URL link, and then you can gain much information here as you wish, and like task description. So it's going to explain what is this data, what sort of attacks, what sort of traffics there are. So the most important part of this data is the features, right? It says like the first column, the second column, or attribute, third attribute. So also you can find the type, continuous, discrete, and so on. So I mean, if you are coming from same background, I mean, networking, that's really perfect, because you can get the ideas behind this features. But if you are new in this area, you don't need to panic, because the task here is classification. All right, so let's consider these are few features, about 42, 43 features. That is going to be the traffic. Let's say each record is going to be traffic. Let's say we are the sender. All right, we want to get connected to, let's say, to your Gmail account. All right, so your Yahoo Mail. So you open the browser and type yahoo.com or gmail.com, and then press enter. Whenever and once you press enter, these bunch of attributes will come together, all right, to collect the traffic and send it over to internet, and networking will be there, right? Means routing will collect your basically routers will collect your request and route it toward the destination. And this traffic goes and comes, right? You transfer traffic, and the destination send back your request. So this is the idea, right, behind this data set. So again, if you're not coming from the same background, don't panic. This is a data with about 42, 43 features that we want to predict the new traffic, come over. Is it normal traffic or attack traffic? And then we usually use it for, that for firewall, for intrusion detection system, and so on. So we can, come back here, KDD Cup data. If you want to know more about, the features, data description, guys, please feel free to go through these links. And this is about, I mean, these are the labels, right? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, about 22 labels, but we want to, and plus normal, yeah, 23 labels there are. And we want to, uh, convert it to the binary classification. Please follow me and let's see how we can do so. So there are two data, right? One is the full data set with 743 megabytes. So guys, please feel free to download. All right, or 75 megabyte. I've done that. I've downloaded both of them, and they are in my drive. So that's the reason. You can also do the same thing. You can hear his file. My files is here. So please have a file. So go through new folder, right? Name it files or whatever you wish, and then you can upload both files here. So one is 17 megabyte, guys. These are zip file. All right, you can see that JZ means this is a zip file. So, and this one just 10% of entire data, which is 2 megabytes. All right, so but the actual data after unzipping is going to be 75 megabyte for this, and 700 something, after unzipping is going to be for full data. So it's up to you that which one you want to go ahead. And I mean, you can find here, this is my drive, right? If you connect to your drive and then my drive, and then files, or you can see that these are here, right? These KDD cup and KDD cup, 10%. You know that. Just click on these three dots, copy the path, and easily paste it here. All right. So let me do a start with with the entire one, because I want to discuss about very important you know trick here. All right, and then we can discuss through it. So let's say I want to load the file, including the entire file, which is the zip file 18 megabyte. You can see that Spark can read zip file. Guys, you can see that here we are saying that .csv. You can also convert it to text, means read it like a text. But let's take it as CSV, because we know that based on data description, we know these data, right, includes columnar, or let's say includes attribute based or label based data set, and each row is going to be uh, a sequence of attributes. That's the reason I'm going to read using CSV. That's really great, guys. In Spark, we can read also a zip file. So header false, because there is no header in data, right? The first record is going to be exactly the traffic. So let's print out first file record and get few more information and this number of partition. So I want to give you a hint that why we need to go through this and why it's so important. All right, so you can see that we said that header false. That's the reason it's going to provide very random header here. All right, and you can say this is first record, right? And then we can move forward to the last column. You can see that this is column 41. It means that the first, because it's starting from 0, right? There are 41 columns or 41 attributes that we want to predict, this column, this attribute, or this label, right? So, and then what we can see here, the original data, there are about 5 million record with big problem. So guys, one partition. So Spark fails to partition zip file. That's a trick. Okay, you must be very careful. So what we can do after reading data in the zip file, so zip file is really great, data type, because you can compress your data and then you can load it in your Spark. But you need to be very careful in this case, that afterwards make sure to repartition your data. All right, so you can use like I wish to have. So because since we know the size, why not to divide it into 6 partitions? And here we have 2 cores, because Google Colab provides 2 free cores for us. And 6 partition will be each partition about 100 something megabyte. I think it's fair enough, right, to do so. So I would say that 6 partition. All right, and then you can check it, right? Get number of partitions. And then if you run it, and then you can make sure that everything is going perfectly in the parallel mode. Okay, guys, because the topic is parallel processing, to avoid single core processing over the entire data. And in this case, we can do something like this. So, but what I want to do for the rest of this exercise, I want to go back here, and then I want to use the 10% of data, because since this is the online coding, right, and live coding, I want to make it really quickly going through these tasks and these steps. And it's up to you guys. If you want to go ahead with full size, okay, you just need to do this repartitioning. That's it. All right, so I want to say that here, if you want to go ahead with the full size. All right, divided to 6 partition. It seems is fair enough. So you can see that it takes time, because it's going to shuffle data and then partition them. So, okay, it's done, right? We have now 6 partitions. So from now on, you can go ahead and you can work with full data. But let me control space. Let me read, 10% of data. All right. And if I run it, perfect. First file. So guys can see that about 500K, somehow 10%. Again, guys, the problem is having one partition, as I mentioned, because of zip file. So, but since the size is 75 megabyte, still one partition is good, right? But still with one partition, we cannot have parallel processing. For parallel processing with 2 cores, because Google Colab provides 2 cores, right? So why not to have 2 cores? Sorry, why not to have 2 partitions? All right. So you can come back here, repartition it to 6 6 parts, or let's say 6 partitions, or let me say chunks of whatever you wish to provide it here. You partition it to 6 chunks. So for the 10% of data, we can do 2 partitions, and then in this case, each partition will take, 30. I mean, about 40 megabyte, right? Close to 40 megabyte. Still good, right? We can go ahead with 2 partitions. Okay, let me run. So then, here we have no labels. We don't have label. Let's add the labels. How we can add labels? With this method, with column renamed. Okay, we would say that instead of underlines C0, please put duration. Instead of underline C1, please put protocol type. Where we collect them? From data description. All right, if you go through data description, right, these are here, right? First one is duration, the protocol type, service, back to back. So, all right, then let me run this one to rename, and then by df.true, we can make sure everything is as we expect. All right, perfect. Can see that the labels, they are. All right, so you can double check. Perfect. All right, and connection status is going to be the labels, all right, that we want to predict. So let's see if labels are binary or not. So we know that they are not binary, because from data description, and also visibly here it says normal, Neptune, SMORP, right? You can see that different labels there are, right? So again, if you're not familiar with this networking data, don't worry, just take it as 42 attributes. You want to use it as independent variable, and you want to predict a dependent variable called label, right? Let's see how many labels there are. So in data frame, let me zoom in. So df select, please give me this connection. It was the label of last column, right? So distinct, please, distinct, remove duplicates. And we found that there are about 24 labels. Let me put 30 and see how many there are. All right, you can see that. So there are many, right? So as we know, as we went through this, this data set, we know that there is only one label, which is normal traffic, and the rest going to be the attack traffic. Let's take this, this mindset here, that taking all these labels, right, as attack traffic, and then just normal traffic for the rest of the traffic. In this case, you now have two classification, or let's say 2 labels for binary classification. How we can do so? Let's add new code cell. All right, and then here, let me say from PySpark.sql.functions. So import. There is a method we call when. Let's see how we can use it. So df, please, df with column. All right. Okay, because we want to work with column. Please have this one when, because I want to write conditional statement. All right. When this df, which column, this connection, let me use control space, this connection status. All right. whenever it's not normal, okay, why I'm writing this with dot? Because here we have a normal dot, right? If it's not normal, please return one. Return one means, okay, return attack means this is one, this is one, this is one, and the rest, everything is gonna be one. Dot. Otherwise, zero. If then else, right? This is the way. So now you have to rename it. So let's do this one. So where to store it? So please store all this stuff into a new column, name it label. That's it. And now let's make sure here that we have binary classification. So please go over label for me, this thing again, and then let's show. All right, and then run it. Perfect. Great. Now we have two labels, right? So let's count them. How many records we have per labels? How we can do so? You need to just group them by, right? df.group by. All right, group by based on label. Okay, means provide two cluster for me, one cluster for label 1, another cluster for label 0, and count them, how many there are. All right. So, and if you run these, okay, we forgot to add show. If you run these, great, you can see that it says traffic, that is label 1. Label 1 means attack. It's about 400K, and about 10K is going to be for normal traffic, right? So, oh, sorry, it's 100K, right? So 100K, I mean, the total is here, right? Okay, if I take this one, all right, if I come down and if I use my calculator, right? And then this 97,278 divided by the total value. So about 20% goes for normal traffic. All right. Based on this one, 20% is going to be normal traffic for normal records, and 80%, guys, this is about, right? About 20% and about 80% for attack traffic. So here, I mean, you can see that it's somehow imbalanced. Imbalance means that one label provides many type of data, but the another one, like normal traffic, provide less number of data. So there are different approaches that you can, you can work around to manage this imbalanced data. So how to work around? So one technique, let's say, dealing with imbalanced, let's say, labels. So you can take them, as your own interest, and you can have a research on this. So let's say resampling. So resampling means that you can apply it to balance the class distribution. All right. So in this case, you can apply oversampling on the minority classes. All right, and undersampling the majority classes. All right, and then you can combine them. So maybe second technique is going to be like, let's call it weighted loss. All right, in this one, I mean, what we can do, you can assign higher weights to the minority class. It means that in this case, to the normal, you can give, the highest weight. It means that you need to add one more column here to give the weight to the minority ones. And then you can give more importance factor during modeling, training, validation to these weighted, uh, let's say the weighted rows. All right. So, or might be you can use data augmentation. So data augmentation means, guys, if you have limited data, let's say we have this data, right? We don't want to do research. We have no idea, or you don't want to do sampling or weighted loss. At least you can generate synthetic sample, means artificial samples for the minority class, means that for the normal one, you can learn the pattern using like smooth method, So means synthetic minority oversampling technique to learn that normal traffic, which is the minority, and add some synthetic data to your data. All right. Or ensemble methods. So ensemble methods, guys, such as bagging or boosting, right, can help mitigate the impact of class imbalance. So these methods combine multiple models trained on different subset of data to improve, overall performance in the presence of this imbalanced data. Or even, if you want to go ahead, evaluation metrics. This is what we want to do on this tutorial, right? Evaluation metrics. So when working with imbalanced data like this, right, accuracy factor may not be the most appropriate metric to evaluate the model performance, all right, because it's not considering imbalance. So what we can do, you can take some evaluation metrics that they are less sensitive to class imbalance, like precision, all right, like recall, like F1 score, all right, even area under the curve that we can use it, all right, to deal with these typical problems. All right, let's move forward. String indexer. So we had this discussion that we can map a string column to a column of label indices. So you need to firstly import a PySpark machine learning, and then features, all right, feature, and then import string indexer. So which column? Let's say on this data, right? This column protocol type, service, and flag, exactly these three. I need these three because these are categorical textual columns. All right, we need to convert them to indices, so to the number. So I'm going to copy these three, and the rest, you can see that the rest, everything is numeric except last one, because last one we don't need it because we created the label column. All right, so here I want to come over here. I want to say that columns, all right, to index. So these are the columns. Make sure to add them as a list. Okay, because I want to write a loop to take this string indexer. So, guys, if you want to take them one by one, you have to say a string. Maybe here you have to say indexer is, a string in indexer, right? You have to say input column. So input column, maybe you want to take, first this one protocol type. All right, and then you have to put output column. All right, output column. Please, like this one, maybe you can keep, like this. And then here you have to say like index. So whatever you prefer, you can put it as the output. And then df is this indexer. All right, fit to the data means learn data and then transform it to data. All right, df show for our reference. You can do this one, but you have to repeat this one 3 times because we have 3 attribute we want to do. You can take it easy, right? For loop for, let's say, columns, for column in this one, right? This is the, very easy loop. So make sure to move them all inside the loop. And then here I want to remove this one and add this column, right? Because we want to take them one by one. Column, and then here maybe you can say column plus, okay, and then you can keep this indexed, and then output column would be like this. And let me run to see the result. So we can see that this green cursor is here, means it's going to fit and transform. All right, and now show, right? The green sign is here, perfect. So just you need to move right, and great, guys. So guys, this is a label we generated, right? We said normal 0, and for the rest, it's going to be 1, right? So you can see that protocol type index, service index, and flag index. Okay, we could convert them to integers. So from now on, we can ignore this one, this one, this one, and duration, because duration is the time, or anything else. If you don't like to take them for modeling for logical reason, you can drop them. So before dropping, you need to find if there is null value, right? Again, from PySpark .sql function, we need to import col because we want to work with columns. All right. So uh, we have to say df select. Guys, if you are not familiar with API coding or even Python, don't worry, you just need to run this syntax easily. All right. But if you know Python, even basic Python is really, great enough. So for C, I want to write it into one single line. In df dot columns means go over each columns and take this C. All right. And then I want to say that calculate the summation of this column C. All right, check if it's null. Let's cast it to integer. Okay, we want to check if it's null, and then also because their output is 0 or 1. Okay, if it's null, it's going to be 1. If it's not null, it's going to be 0. We would say that convert it to integer. And why not to give a name? So what you have to give a name? Let's say C still column can be good enough. So guys, but one thing, this is functions. If you use sum, this one, you will get error. Okay, at the end you can say, okay, let me say missing values. All right, and the missing values, the show. All right. So if you run this, you would get error, right? Let me run it. So you know why it says non-iterable column is not iterable? You know why? Because sum here is going to be the sum method in Python, not in PySpark. We need to run this sum in the parallel mode. Because of that, we need to import it from this function, okay? Because then from now on, sum will be the parallel mode computation, all right? And then you can run it now. So you can see that there is no missing value. That's really perfect, right? That's super, right? But if you get, you know, this problem of, null value, you need to replace. One technique for replacement is, imputer technique, right? Which is available in machine learning library in PySpark. Or you can use, if you wish, you can use feed NA, or you can use, drop NA, right? And last one, this imputer imputer from this one, PySpark .ml .features. All right, you can import that feature. So guys, please refer to my previous videos about dealing with null values. All right. So then let's move forward. Okay, guys, another trick here is we need to consider features against each other to see if we can find linear separability. Why we need that? Because logistic regression is going to provide the let's say S shape, or let's say the curve, like the S format, right? Like S format. And this curve, right, is going to be very important for us because logistic regression, you can see that, right, is going to be like, this. Let me click on this one. So we wish to have this one right at the end. It's going to be the curve, or S-shaped curve, right? So, and this is just, one feature, X, but here we have 41 features. So if we have many features, we should expect not great outcome for logistic regression because they affect negatively on each other. And to do not affect them negatively on each other, you need to find firstly, are they correlated or not? If they are not correlated, means like X goes left side and X1 goes left side and X1 or X2 goes on the right side, two different directions, it's going to be the good sign. All right. So for instance, here, let's say, I mean, So this one, let's say this source byte. Okay, let me this one source byte. So it seems one of the most important features here because we have numbers here, right? I mean, 7,000 something, 1,000 something, and 300 something, and 00. So you can, right? You can check the linear separability of these features once the class is 0 and once the class is 1. Because for instance, I mean, this data, if you go to right side to find the label, so you can see that it says 0 and then 1, 1, 1, right? And if you come back here, so if you can check between these three, if it is really linear separable comparing to this one and this one, because they are coming from two different classes, you can take this feature, one of the most important feature here, because it's going to provide linear separability. All right, so how we can do it, you can compare the average and the standard deviation. All right, so we can gain insight into the distribution of these source bytes and assess its potential linear separability. So let's say that lower overlap and distinct statistics between the classes generally indicate better linear separability, right? This is the idea behind that. So how we can do it is going to be really easy. You just need to come over here. So please do it over, you know, as many as column that you think you need them, because guys, here we have 42 columns. Taking all columns might resulting in not appropriate, outcome, not great enough, not optimal, predictor. All right, this is really a trick that we have to consider and we have to apply. So how we can do that? Let's say I want to name it class, 0 stats, for instance. All right, and then I want to say that df, please filter what to filter. Df label, all right, please be 0, means normal traffic, and then select. Okay, means go over those data frame that label is 0, and then select. What to select for me? I want to calculate the average of what column, the average of these columns, source bytes. Let's, alias, rename it to, let's call, average source bytes, something like this. And comma, let me go next line for readability, and also standard deviation, please, for me. Okay, well, maybe I can, take this one and put it here, right? And this one's going to be standard deviation. Okay, and not average, is one standard deviation. All right, so guys, make sure to import these two methods. Otherwise, as I said, Python will take them over. We need to take the parallel mode format. It means that from PySpark .sql functions are please import average and standard deviation. Okay, so I want to say that this is average and standard deviation for class 0. Okay, I wanted to copy the same thing, come over here and say class 1. So this is just for source byte, right? So I just want to change 0 to 1. That's it. So what I want to do now, I want to say that print, for instance, class 0 distribution. All right, and then print, let's say, the average source bytes is going to be, you know, uh, this one. Okay, and then which column? This column. Okay, and then let me paste here, average, no, standard deviation. Okay, I'm doing, okay, this one, average should be here. Okay, and some deviation there. And you can do this one, right, for the second class, class 1, right? So Okay, I mean, I think it's better to add 0 because mentioned this is class 0 and this is class 1, right? And this is class 1. So it means that this one should be class 0, right? Class 0, class 1, class 1. That's it. And make sure to convert this one class 1, right? Class 1, class 1. Maybe this one, or maybe, I mean, just changing 0 to 1 would be enough. But let's keep it like 0, 0, right? Just like a hint for us. All right, so we need to get them as a method then here, right? So then we need to get them as the dot notation. All right, as a dot notation. Let me run. But still, there is something wrong. Let me double check. So maybe here, because we have to, maybe you can say collect, or maybe here I can just say first, maybe just first value for us, because we don't need to take all, just first value. All right, and then if you run, okay, it seems it's working now. All right, great. So I'm also wondering if I am able to convert it to bracket notation. Okay, bracket notation. All right, great. So as I as I was expecting, right? Even dot notation works, guys, and also this bracket notation works. So both works here. So let me run again. So what will be the result? How we can interpret? So these numbers are big numbers, right? You can see that it says the average source byte for class 0 is 1000 something and 34K for standard deviation. For class 1, you can see that what's going on. What we can achieve, if an average are significantly different, you can see that is 1000 something, this is 3000 something, right? It suggests that there may be a distinction between two classes. This is really great news here, right? Even you can compare it for standard deviation. 34K is gonna be like 1 million. So guys, we didn't normalize data, right? So that's the reason these numbers are really huge. So it shows that these column, right, this source byte is going to be really perfect column for linear separability. So why not to apply this, this, I mean, bunch of code to now is source byte converted to like destination byte converted to wrong fragment. I mean, do all this stuff and try to find which column is going to affect negatively on linear separability. It means that they want to have similar averages or similar standard deviation. Then you can decide to ignore them for modeling, for processing, the rest of processing, or maybe you need to keep them. If you keep them, you have to expect some, some, let's say, not accurate outcome at the end. All right. So vector assembler, prepare the feature column right into a single column. Guys, we know this one. We discussed in the linear regression video and linear regression class. So, but you need to bear in mind something. If I say df print schema, guys, all of them string, 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 right? These are all a string, but just these are integer double because we could add them here, right? But the rest are a string. Vector assembler do not accept a string. You need to convert the type, the data type. How to convert? Let me come over here. Right here, I want to say that. So from PySpark. Okay, we imported, but let me add it here. Maybe you need to know what going to be column, right? Because the column means col, we need it. So again, I want to write a for loop to do over all column for column in df.columns. What I need df with columns. Please go over each column, the code of this column, okay? And what to do, cast it. Let's cast everything into double and return it as it is, as the column. That's it, right? So run it. All right, and then let's make sure that we have all changes. Not yet, right? You can see that these are all a string. So let me double check. Okay, we need to overwrite it, okay? Like this. Print schema. Great, guys, can see that double, right? Now we can use vector assembler. So for vector assembler, where are you? Okay, it's here. So what I want to do for vector assembler, let's say that assembler is going to be the vector assembler. All right, so you need to provide the input columns. All right, and then you need to have the output columns. So what is vector assembler, guys? We discussed in the linear regression. Linear regression tutorial. Please make sure to watch that video again if you haven't done, or if you need more information. So we still need to do this input columns, and then data is going to be assembler, right? Dot transform. Please transform it over data. That's it. You can double check. Data is data. Let's select what to select. Just select these features. This one and the label. That's it. From now on, we need features and label. All right. So, but what to import? So let's say that after taking this calculation, this, linear separability check, you want to come over here. Let me copy just, guys, few of them randomly. Let me just copy like this stuff here. Okay, let me just copy. Okay, let me come over here. And here we go. So, all right, maybe I can take, Notepad and paste it here, right? And here, copy this one and replace this one. Please replace it with like something like this. Replace all. All right, and then copy again. Because guys, you know what I'm going to do? Instead of taking all this one by one, right, like this, to take them one by one, I made it really easy. I said, okay, let's just, replace the values. Okay. And here we go. The last one, make sure to add for last one and also the first one. The first one. So guys, these three, we don't need them because these three are now, textual. Drop them. Let's say you want to go through this one. Let's say, like, I don't know, let's say these are the column. You found that there is no linearity. You want to drop them, right? So maybe I don't need that. So guys, I'm taking this stuff, randomly, right? So maybe, maybe these two as well, right? Maybe this one as well. So connection status, guys, make sure to drop it. We don't need that. Label and the rest of the things. All right. So let's take all this stuff together. And why not to have, this one into new line for readability, and then make sure how many we have. All right, there are many. So what I want to do, let me also drop this ones. Okay, let's say we don't need this three. This three. All right. And that's it. I think everything is ready now here, and this one at there. Okay, let's say we have these inputs, right? Make sure to remove label also. We don't need label because label should be separate, rough label. That's it. Okay, data is ready for having all together in one single and the data.show, right? Let's say 5. All right, so these features goes for, you know, having them all together into a single list. So not visible, what we can do, maybe here I would say data.show 5 truncates false. All right, and then we can see visibly. All right, great. So what we notice here, very, very nice. I mean, uh, let's say representation in PySpark. We call it sparse vectors. Okay, what is this? So if you notice here, we cannot see the entire data, right? Because we are expecting to see all features here back to back, but we can see just a few, you know, numbers, what they are. So 31 means that here you have 31 attributes, this one's 31 attributes. It says that out of these 31 attributes, these are the indexes and these are the values that they are not zero. It means that other indexes, you know, other indexes like that you took them, let's say, I mean, you took them, right? Those are null values, right? So for instance, it says that first record, all right, the first record that picked up, right? Just these indexes are not zero, that these are the values, right? Let's say for this row, these are the indexes that the values are not zero, and the rest gonna be zero. So why we have these sparse vectors? This is the compact representation that store only non-zero elements, right? I mean, this is really advantage when dealing with high dimensional data, and let's say where most elements are zero, it will definitely reduce memory usage and computational complexity, guys. So, but if you want to change your mind, and let's say that, and let's say for any reason you want to see, you know, the entire data, right? All right, if you want to see the entire data, you can do something like this. Let's say you want to say, no, I want to read all data, not just non-zero values. All right. So what we need to do here, we can say extract the values from, let's say, from sparse vectors to the list format. Okay, how we can do it? So here, this data, right? We can say data, please limit to 2. Just let's get first 2 records, all right, and then collect it. All right, let's name it selected data. All right. So then here, so guys, this is additional consideration, right? I'm not recommending you to do so, but if you wish to see data, please do it. For row in this selected data means going to be 2 records. All right. What to do? Let's say dense vector is going to be row. Okay, the first one dot to array, please, and print it. Okay, and then print it. Print, you know, this dense vector. Let's see. Or maybe, okay, I'm doing wrong here. Maybe here you have to say select just, you know, the features for me. Okay, this one for me. Let me start with features for me. All right, and if you run, all right, now you can see that, right? You can see that how going on, you can see that 0, 0, 0. That's the reason it's going to ignore them, right? And that's the reason it's just indexes start from 15. You can see that 15, 16, right? Or maybe this is not coming for the first one, right? I'm just going to give you information that what does this 15, 16, 17 means that, right? So that's the reason, since there are many zeros, he's going to ignore them and just print out non-zero values. This one helps to avoid, you know, lots of zeros to be printed out. So next step, guys, next step is a standard scalar, right? We need to normalize data. Again, if you're new on this area, on this topic, standard scalar, please watch my previous video about linear regression. Okay, scalar. It's gonna be standard scalar. So input column, please input column be features. All right, and output columns, please. Let's call scaled features. All right, so that's it. And then scalar model. Scalar that fits to data, right? And then data is gonna be scalar model that transform to data. And let's see that for this data, we just need to get these scale features and label. That's it. These are what we exactly need that, all right? And then let's print it out. Data.show. Just 3, and let me say truncate false. Let's see. So I need to insert code because we need to split data, right? Split data. So perfect. So can you see that this is the data? You can see that they are now in the normalized format, right? And the label and the label. So split data. So train data and test data, right? So data.random split, please, right? So we would like to get 70% for training, 30% for testing. Why not add seed if you want to have, you know, the same, I mean, splitting as I'm doing here, okay? Run it to make sure they are over there. Now we need to come back here and apply regression, right? Data is ready now. Okay, data is ready. We need to start working with LR, logistic regression, logistic regression. All right, I need you to take feature column. Which column? Scaled features, please. And what about label column? Label column, please. E label. So guys, since the backend of logistic regression is still linear regression, you can add this reg param. This is for regularization parameter in linear regression, and elastic net param if you want to consider lasso or I mean reach for regularization in your modeling. All right, so it's up to you if you want to apply. But what I wanted to add here, guys, threshold. You remember we discussed about threshold. So threshold, the default is 0.5, right? If you wish to change it, right? Let's say I want to, let's say after all data, I mean, this is splitting. I want to get 0.4. You want to manipulate it, right? You can get output. If output is not appropriate, let's say you get accuracy like 82%, guys, not really great. Maybe you need to come back here and change it to default, or maybe you need to increase it, right? To move this threshold up and down. Let's take it 0.5 as it is. And why not for this reg param? What happened here? Okay. And then for this reg param, right, which is, uh, I mean, control regularization in linear regression, I wish to use, you know, 0.01. It's up to you because we need to tune these attributes, right? We have no, like the optimized one, we have no in hand, the optimized one, you have to tune them. So let's say to fit them on the train data, please. All right, and then LR model. Let's say LR that fit. Uh, so yeah, maybe, I mean, this one, I would say LR model, I mean, logistic regression model, please fit it. And then LR model. Now transform it. If you wish, you can transform it on train data, right? And then here you can say prediction, all right, on the train data. Or you can take it, also here as a test data and measure the blind test data. So guys, this is just for, you know, uh, to check the accuracy on training and testing separately. If you wish, you can do it. For this tutorial, we want to take just testing data because testing is important for us to evaluate the performance of this model because we train already data, right? The training data. So let me say that the test one, please select just to make sure everything is as we expect. The label, original labels, and the prediction. So it means that whenever it's going to fit data, it's going to and transform testing data, it's going to add the new column called prediction. The prediction would be, I mean, the result. Let me just print out the first 20 rows or 30 rows as how many you wish. Let me run it to see the result, just, to make sure everything is going perfectly. All right, it's done, right? This stage is done. And we are here to see this first 20 record for testing data. All right, great. So what we can see here, like these are, it seems, that perfect prediction. But here label is 0, we predicted 1. Label is 1, we predicted 0. Can see that there are lots of misclassification. So for this misclassification, guys, as we discussed, you need to play around with these parameters, right? And change them also, the lambda that we need, that this reg param, right, for regularization. So this reg param works for, for both regularization applying on linear regression and logistic regression. You might need to, change it, right? But let's drill it down because these are just 20 rows. So how to evaluate the model? So if you remember, we discussed about confusion matrix, right? Let me add confusion matrix. So how to add it here? I want to say that confusion matrix, please, these LR prediction testing data. So we need to group by, right? Please group by. I need to get them into 2 groups, label and prediction. So then count it. That's it. And if you want, you can also order, right? Order, or maybe you don't need order, right? Just let me see that confusion matrix. Not sure. So this is just, guys, for testing data. You can do the same thing for training data, right? To check the result. So what we can see here, so perfect, says the label 1, prediction 1, this is true positive. This amount of true positives, right? So 0 and 0 means true negative. So label was 0, but we predicted 1 means this is false positive. So how many? 458 out of, 5k, some, not 5k, you just need to calculate, the summation of these four and then calculate how is that gonna be, I mean, based on the percentage. Or if you wish to see it into the confusion matrix format, you need to convert it to pandas. So guys, this data is now small data, right? It's easy, that's even small data. This one, I'm going to take it and convert it to pandas, leads to pandas. All right, so why not to say confusion matrix pandas, something like this. All right, so this one, so you need to use pivot, guys. Pivot, uh, return reshaped data frame, right? Organized by given index, column, and values. It means that I want to get label as the index. I want to get, this prediction as the column, and I want to get count, these four, as the values. It means you need to use pivot to shuffle it. So index is going to be label. All right, columns is going to be prediction. All right, and then values is going to be this count, right? You can see that this count is here. That's it. Let's run. Perfect, guys. I think it's now much better, right? It means that 1 and 1, many, 0 and 0. So the errors goes here, right? It was the label, actual label is 0, but we predict 1. 458 means false positive, right? And this one is false negative, right? So why not to go through those, you know, uh, let's call that the additional, let's call additional performance metrics that we need them, right, to evaluate the correctness and the robustness of this model. So please, LR prediction test, okay? Please give me the labels, those labels that are 1, right? Let me write 2 condition. So this is 1 condition, and this one, not the label, the prediction is 1. So what we call it, guys, we call it true positive, right? Label is 1, and also prediction is 1, right? It means, for instance, it's going to be this one. It's going to be this one, right? 1 and 1. We have to count them, right? It means that these are the condition. So please get this one, get them as the index, and count them. That's it. So I'm going to copy, Control C, Control V, Control V, Control V. True positive. Let's say false positive means label was 0 and we detected 1, and this one false negative means it's 1 and we detected 0, and false true negative, oh sorry, yeah, true negative means 0 and this one 0. All right, so then you can come over here. So you can see that true positive will be this value, right? But here we want to collect them, right? We want to collect them. So then accuracy. Accuracy is, if you remember from the formula, true positive plus true negative divided by true positive, false positive, false negative, and true negative. If you remember from precision, it was true positive divided by true positive plus false positive, right? And if you remember recall, it was going to be true positive divided by true positive plus false negative. And F1 score was 2 multiplied by this precision. Let's go do like this, 2 precision multiplied by recall. All right, and then divided by this one. All right, but should be this side. So now let's print the result. Okay, print, let's say accuracy, round this accuracy to 2 decimal, right? Let me 2, 3, and 4, right? And then let me say precision. All right, recall, and F1 score, and you can change it to precision, recall, and F1. Let's do those ones. And really strange, guys. I don't know what happened, but this is what we have. Maybe you can here multiply by 100, right? And multiply by 100, multiply by 100, multiply by 100, and just here say 444, and then you can see included, percentage format. So you can see the accuracy 98%, 99, 98, 99. So based on this result, it's acceptable result. Unless you are expecting even more than 99 for recall or accuracy. In this case, you need to manipulate and you need to play around with input parameters like lambda, training rate, learning rate, and the threshold, and so on. So guys, this is all we did for logistic regression with all consideration.